All right, so today we're going to look at 3.2, which is on 3 different topics, all kind of connected. One of them is called continuity, then the intermediate value theorem, and the last one is end behavior. So a lot of times when you try to draw something on the calculator, it assumes that what you want to draw is connected. Okay? So here's a graph of something that we haven't studied yet, but it is definitely not connected. Okay? It's in several different pieces. Now, if you had an older calculator and you tried to draw that, it wouldn't know that they're separate pieces, and it would try to connect them all. So it would look something more like this. Let's go. Let's see if it does it. Yeah. See how it's trying to connect them? That shouldn't be happening. These are definitely separate pieces, and the way I drew it the first time was the correct way it should have looked. So depending on your calculator, mine do this, but depending on which one you have, if it's older, it might try to connect things that shouldn't be connected. Okay? But newer calculators have an option to detect what are called asymptotes. It takes a little longer to draw it. Notice it is slower, but it is drawing it properly. Okay? It's not trying to connect anything that shouldn't be connected. So now let's try this one. 1 divided by x minus 3. What number are you not allowed to plug in here for the domain? Yep? 3. So when you get to 3, watch what happens over here. Kind of goes a little crazy, right? Can't connect when you get to the number 3. If you were drawing this on an older calculator, it might try to connect it like that. And that is not how it's supposed to look. So what's important to understand there is that's a graph that is discontinuous, meaning there is no way to draw it in one shot without lifting your pencil. Okay? You would have to lift your pencil, put it in a new spot, and then draw the second piece. So this graph is 2 separate pieces, and it's very easy to see it's 2 separate pieces. Okay? There's a big asymptote right in the middle of it. Okay, let's try this one. The integer function. Okay. If you go to math, I think we did this before, it's a step function, number, and the 5th option down is integer. Remember, this function rounds everything to the biggest integer it can that's smaller. So like 4.9 would be to 4. 4.8, 4. 4.2 goes to 4. Basically, it chops the decimal off. That's what it does. And if you graph that, that's another example of a graph that is not connected. Okay? Different reason why it's not connected than the last one. Has nothing to do with dividing by 0. It has to do with the fact that this function rounds. So it does not allow any decimal values in the range. Because there's no decimals, you get gaps. Okay? All you get in the range here are integer outputs, no decimals. That results in discontinuities. Now, this one is very different. I'm not going to draw it, but that's just a parabola. It's a U shape. That one you could draw without lifting your pencil. Okay? The first 2, you can't. So the name for that is continuity. So we say that a function is continuous over an interval starting at A and ending at B if it's possible to basically trace from A to B without ever lifting your pencil. So it is possible to have a function that is continuous in some spots, but maybe not in others. So let's say you had something like this, and then it continued on like that. Well, if you tried to trace from here to here, that's continuous. You could definitely do that part without lifting your pencil. You could trace from here to here without ever lifting your pencil. That's fine. But if you tried to trace from B to C, you can't do that, right? From B to C, there's a break in the graph. Okay. Any question on that idea? All right. So if you can trace without lifting your pencil, then you have a continuous section. If you do have to lift your pencil, then it's discontinuous. So as I said before, you might be able to find some sections that are continuous and some sections that are not. So let's look at an example. And let's write down two intervals that are continuous and two that are discontinuous. Start with continuous. Remember, when you describe an interval, you have to describe it in set notation and give me a start value and a stopping value. Okay. So I'm going to graph 1 over x. Okay, what number are we not allowed to use for x in this one? Bless you. Yep. 0. So again, dividing by 0, a lot of the times, not all of the time, but results in a vertical asymptote. All right, so let's take and look at that. And could somebody give me an interval that I could trace through and never lift my pencil throughout that interval? Jackson?
What was it?
So I'm looking for an interval in that graph that is continuous.
Oh, negative infinity to 0.
So you're going to trace, can you tell me how you would write that?
Open parenthesis,
Yep.
negative infinity,
Okay.
0, open parenthesis.
Yeah, so that is an interval that is unbounded. And if you had enough time, you could trace from negative infinity up to, but not including 0, and never have to lift your pencil. Can somebody give me a bounded interval that you could start and stop and trace that section without lifting your pencil? Raj, could you give me one?
Closed bracket.
Closed bracket, sure. From where?
1 to
Sure, 1 to 3. You could definitely trace from 1, starting at 1 to 3, and never lift your pencil on that stretch. Yep. So that's a continuous interval. All right. Now let's do discontinuous. What would be an interval that I would be discontinuous in this graph? Lens?
would it be open in parentheses, negative infinity, comma, 0 with a bracket?
So
Because you're including the 0, which is
yeah, we can't. Yeah, so 0. Let me think about that one a little bit. Can you give me one that stops at a little bit different point? Sure. So to be discontinuous, you have to pass through 0 in this one. If you just try to get to 0 and don't pass through it, you're trying to end at a number that's not part of the domain. So I'd have to think about that a little bit. That's kind of a little bit of a tricky one. But I'd have to think about it. But that's definitely discontinuous because you're starting on a section, you're lifting your pencil, and then you're drawing more, but you had to lift your pencil to do it. Can somebody give me another interval that's discontinuous? Yep, Ethan?
Could you just go from like -3 to 33?
Negative what?
-3 to 3.
To 3, yeah, -3 to 3. Anything that passes through 0 is discontinuous. Okay. So now let's think about the integer function. Okay, let me put that one back up. I want to know the length of the longest interval in this graph that is continuous. So what's the length of the longest interval that you could find that is continuous? Whoops. Well, just look at it. Yeah. Yeah, it's just 1 unit, right? That's the longest interval that you could ever find in this graph that is continuous is 1 unit long. There's no interval longer than that that is continuous in this particular graph. So they're not asking you to write a unit in this one. I'm sorry, they're not asking you to write an interval. They're just asking you to find the length of the longest interval, and it's 1 unit. So there are really 3 different ways that you can have a discontinuity in a graph. The first way that you can get a discontinuity is you have an undefined value in the function. Undefined value, like for a rational function, would mean you tried to divide by 0. Dividing by 0 will give you a discontinuity in the graph. Sometimes it's very obvious to see, like this. 2 divided by x minus 3. X can't be 3. So when you get to 3, you can see very clearly it doesn't connect. Okay? So that's one way you can get a discontinuous function. Another way you can get a discontinuous function is if your graph has a break in it. Okay? A break isn't due to dividing by 0. This particular function has breaks in it because of rounding. So it just causes the answers to jump. And the third way that you can get a discontinuity, and it's the most tricky way to see, is it having a hole in the graph. If I graph that and put it in parentheses, so x squared plus 3x plus 2, and divide that by x plus 2. What number are you not allowed to plug in for x? Yeah, you can't plug in -2. And if I go to my table, I can verify that. If I plug in -2, I get an error because I'm trying to divide by 0. But look at the graph. Does it look like anything weird happened at -2? You think? No, it doesn't look like anything happened. And that's because a hole in a graph is infinitely small. So you can't see it when you graph it. Even if you zoom in, you can't see it. Okay? If we were going to sketch that graph to show that there's a hole in it at -2, you would do something like this. You put an open circle on the graph, right there. And if I could, I wouldn't even draw inside the circle. So if I was doing it by hand, it would look like this. That's how you draw a graph with a hole in it. Now, why is there a hole in the graph and not that vertical asymptote? Because if I change this number, instead of making it a +2, make it a +3. Just change it a little bit. Watch how the graph looks now. Totally different. Okay, just change that one number and it made it very obvious that they don't connect. There's no longer a hole in the graph. Does anybody know why this particular graph has a hole in it? Yep.
Is it because there's a 2 on the top and a 1?
Not necessarily. These don't always have to be the same to have a hole in it. But yeah, in that one there is a 2 in the top and the bottom. But it does have something to do with the top. How could I rewrite the top? Yeah.
X plus 2 times x plus 1.
You could rewrite the top, if you factor it, as x plus 2, x plus 1. If you have a rational function, right, fraction, and there's a common factor in the top and in the bottom, that will cause the undefined value to be a hole. So essentially, it's kind of like these cancel out. So if I were to draw x plus 1, let's put this back the way it was. The graph of x plus 1 is going to look identical to that graph in blue. But there's a big difference. The graph in blue has a hole in it. The graph in red does not. Okay. So that's how you can tell that a graph has a hole, when there is a common factor in the numerator and the denominator. That's why when I change this to a +3, I messed up the factoring. If you make that a +3, it does not factor as x plus 2, x plus 1 anymore. So now there was not a common factor. So a hole is really another type of undefined value. Okay? It's kind of like the first one. But it's just not something you can see on a graph. You have to look at the original problem and factor. All right, when we are dealing with polynomials, okay, if you remember from yesterday, the domain was all real numbers. Every polynomial that we draw is continuous. It's continuous everywhere. Right? So if I had you draw a parabola, and I said to you, find a section that is discontinuous, you can't. A parabola is a polynomial, and it is connected from start to end. Never lift your pencil the whole time. Okay, a cubic looks something like this. When you draw it, never lift your pencil. So if you have a polynomial, it will be continuous everywhere. And if it's continuous everywhere, then it's called a continuous function. So if you had a graph that looked like that, and you put different points on it, I can find sections that are continuous, like from A to B, that is a continuous section. C to D is a continuous section, but this is not a continuous function. Continuous function means you can start anywhere, stop anywhere, and never lift your pencil. That's not true here. I can't go from A to D without lifting my pencil. Or B to C, or A to C, any of those. So, any question on the difference between a continuous function versus just maybe a section that's continuous? Okay. All right, so that's it for the first part. That's continuity. Okay. Intermediate value property, or intermediate value theorem. Okay. This is going to tie in with continuity. All right. So to understand intermediate value theorem, think of this situation. If I had a pot of water on a stove, and it starts at, let's say, like 80 degrees. Not that warm, but just 80-degree water. And I heat it up to boil. How many temperatures does it go through when it starts at 80 and it reaches 212, which is boiling? How many different temperatures would it go through? Yeah? Infinite. Right? It goes through every single possible temperature between 80 and 212. At some point it'll hit 90. At some point it'll hit 93.4. At some other point it'll hit 106.125198617. Right? It's going to hit every single possible number you can between 80 degrees and 212 degrees. And that's because boiling water is a continuous process. Right? It can't skip anything from where it starts to where it stops. Now, if I had objects and I were counting them, let's say I started with one object and I counted up to 20. 1, 2, 3, 4, 5. Have I gone through every number between 1 and 20? No, that's a discontinuous process. Right? I never counted 2.6 or 3.415. Right? I didn't get any of those numbers. So, first thing to understand is the intermediate value property is going to apply to something that is continuous. Right? And what it basically guarantees is that if you start at a certain value and you stop at a certain value, you are guaranteed to go through every value in the middle. That's the intermediate value theorem. So now I'm going to write that not about boiling water, but more about a function. So let's say that we have a function that is continuous. Okay? If it's discontinuous, this idea doesn't work. But as long as you have a function that is continuous over the interval from A to B, it doesn't have to be continuous everywhere. Just you've got a section that's continuous. Then, if you find the y value when you're at A, and you find the y value when you're at B, I guarantee you will go through every y value between the two. You might even go through more. I can't guarantee that, but I can guarantee you'll go through all of those. So if you have a point that starts here, let's call that A f of A, okay, x and y value. This point over here has an x value of B, and the y value, well, plug it into your formula and find the y value. If I trace from this point to that point, no matter how I do it, I'm going to go through every y value between that one and that one. Whether I trace in a straight line, I went through every single y value between the two, or I could curve around a little bit. Still going through every y value. Sometimes I'm going through the same y value more than once. And I could even go through y values outside those. I do this, I go way down here, and I go like that. I still went through every y value between here and here. Right? If you kind of imagine like horizontal lines like that. I covered every y value in that zone. And I covered even more. I went way outside it and way below it. Well, I can't guarantee that you'll cover more. Not always. The first two I didn't. But I will always cover everything between those dotted lines. Because it's continuous. I can't lift my pencil. And I got to get from here to there. Okay. Any question on that? So that's the intermediate value theorem. Okay, only applies to continuous functions. Okay, so let's look at this one. So here, it's not as much about finding an answer. It's more about understanding the theorem and why it would work. Okay. So first of all, is this a continuous function? Y equals 3x minus 4. Oh, Dario, what do you think? Yeah, it's just a linear function. So it says to find a value over that interval that you could plug in for x and get 15 for y. So the first thing I want to do is see if that's even possible. Right? So we have an interval we're looking at from -10 to 10. Let's plug -10 in for x. Let's plug 10 in for x. That's going to tell me the values that I'm guaranteed to go through. Let's see if 15 is one of them. Okay. If I plug in, start with -10 for x, what do I get from my formula? Let's.
The result as you know, like would be -34.
Yep, -34. And what if I plug in +10? Oh, we're in. So if we plug in +10, what do we get?
Wait, sorry. I like really want to say.
So for plugging in 10 for x
Oh.
in f of x, -4,
Oh,
26. So what y values am I guaranteed to go through as I travel along that line from an x value of -10 to an x value of +10? So it's a continuous function, and we have two values for y that we're starting at and stopping at. So I'm guaranteed to go through which values over the interval from -10 to 10. Yep. Yeah, I'm guaranteed to go through everything between -34 and 26, even if I didn't know this was linear, but I told you it was continuous. If you start at -34, you stop at 26, and you never lift your pencil the whole time you do it, you're going to go through every number between those two. Okay? They want to know if I'm going to go through the number 15. Will I pass through 15 at some point between -10 and 10? Yeah, right. Because 15 is between -34 and 26. So now I know that I'm going to pass through 15. Let's find where. That's not really important. But the reasoning of why I'm going to pass through 15, that's important. If that reasoning doesn't make sense, then the next question won't be able to do it. Okay. So now we know we're going to pass through 15. So set that equal to 15 and solve it. We get x equals 19/3. And that's, what's that, about 6 1/3, which is definitely between -10 and 10. But we already knew we were going to pass through 15 because of that. Now, if I was starting at -34 and stopping at 5, then I'd say, no, there's no guarantee I'm going to pass through 15. Maybe I could if I go like outside and come back or something. But is there a guarantee? No. There wouldn't have been. Any question on that? All right, so let's look at this one. So this question isn't about finding a zero. I want you to prove to me that one exists. So let's start with this. what kind of function is that? Or just looking for something very general. What kind of function is that? Yeah?
Would it be a continuous function?
That's what I was going to get to, but it's a polynomial, yeah, which is a continuous function. But yeah, no, you were right. So yeah, it's a continuous function. So we know it's continuous, so that means the intermediate value theorem applies. All right. So I want you to prove that this graph is going to cross the x-axis between these two numbers. Where does it cross? Don't care. Don't want to know. I just want you to prove that it will. How would you prove that this graph is going to cross the x-axis between those two numbers? What do you think you'd have to do? Yeah?
Would you have to plug in 0.25 and 0.75 into two different equations?
Where would you plug them in?
Into the function, I mean.
Yeah, let's plug them into the function. So let's do 0.25 first. So let's do 0.25 raised to the fifth plus 2 times 0.25. Let's do that part. And then subtract 1. Okay, so that's about negative 0.5. And let's do f of 0.75. So 0.75 raised to the fifth plus 2 times 0.75, and then minus 1. Okay, I get about 0.74. Okay, so I've plugged them each in. Now what? Yeah?
Now we can find the location of again, what was the number again? Where there's a 0.
Okay, so we're not going to find exactly where there's a 0 in this one. So all we're going to do in this one is prove that the graph must cross the x-axis between these two numbers. And we have enough information now to prove that. We just have to know how to understand what that's telling us. Yeah?
0 is between those two numbers. So.
Right, 0 is between these two numbers. You are starting at a negative y value in this interval, and you are ending at a positive y value. If you go from a negative value to a positive value, and you never lift your pencil doing it, you're going to have to draw through the x-axis at some point. And that means you have a 0. So that's what we want to write down. So we put since f of 0.25 is a negative value, and f of 0.75 is a positive value, and our function is continuous. That's important. If it wasn't continuous, this all goes out the window. And f of x is continuous. So since that's a positive value, f of 0.75, and f of x is continuous, you must pass through a y value of 0 at some point. There's no way you could not. So you're starting at negative 0.5. It's like down here somewhere, or actually we're at 0.25, so it's like over here somewhere. And you're ending at 0.75. Well, or 0.74. So you're going from negative 0.25, or negative 0.5 to 0.74. So you're going from here to there. And it's continuous. How is it continuous? Who knows? Maybe it does something like this. But the point is, you're going from there to there, and you're never lifting your pencil. So you have to cross through the x-axis to do it. You could even cross through the x-axis more than once. Maybe your graph does this. Well, that I don't know. I can't guarantee you're going to cross 5 times, but I can guarantee you're going to cross 1 time. Okay, so any question on how these two numbers, because they go from a negative to a positive, prove you cross the x-axis? Now, if you wanted to know where, well, that's easy. You just do the calculator, second calc 0, and then you can find the actual answer. But this wasn't about really finding the answer. All right, so that's intermediate value property or theorem. Okay, so last thing. So end behavior. End behavior is going to help us when we are sketching polynomials to know what the ends of the function should look like. And we've already been talking a little about it, kind of as we've looked at polynomials. When you draw a parabola and you look at the ends of it, do you have one end go up and one end go down? Or do they both go the same way? Yeah.
They're both going to say.
Right, they both go the same way. So that's what we're trying to figure out. Does one end go up, one end go down, or do they both go the same way? So we're going to talk about how we can describe the end behavior in 2 different ways. One is with arrows, which is not really that formal. And the other one is in what we call limit notation, which is much more important to understand. So here's a graph of y equals x cubed. The behavior of it is down on the left, up on the right. Left side goes down, right side goes up. If you want to write that with arrows, you can describe it like this. Left arrow is describing what's happening on the left side. The right arrow is describing what's happening to the y value on the right. Okay, so we're describing what's happening to the y value. Is it going up or is it going down? There's only 4 different options for polynomials. You can have a down, up, down, up, down, down. Those are the four different things that can happen. This arrow I'm going to describe in a different way right here. And then I'll do this arrow right there. Okay, so let's pronounce this exactly the way it's written, and then I'll word it in a way that hopefully is easier to understand. This says the limit of f of x as x approaches infinity is, and the bottom one says the limit of f of x as x approaches negative infinity is. So what does that mean in words? F of x is another name for y. Limit means what's happening. So what's happening to the y value as x heads to the right? That's the top one. What's happening to the y value as x heads to the left? Negative infinity is to the left. So in this graph, what's happening to the y value as you head to the right? Ready? And what's it going up to? Infinity. That is the limit notation for describing what's happening. Whoops, I did that one. Sorry. Let me fix my colors. But you were right. This is the one on the left. That's the negative infinity. This is the one on the right. The right is towards positive infinity. So as x heads to the right, the y value heads up forever. What about as x approaches the left side? What happens to the y value there? Yeah,
Approach negative infinity.
that approaches negative infinity. Yep. So this one, the bottom one, is describing the left arrow. The top one is describing the right arrow. Okay, so there are 4 different kinds of end behaviors that you can have. Okay, I'm not going to write all of these in limit notation. I'll do one more. I'll do the upper right one. That's the behavior on the left side as you approach negative infinity. So if you wanted to describe that, you would say the limit of f of x as x approaches negative infinity is negative infinity. It's going down. If you wanted to describe that one, that's the right side because it's after the comma. It's also going down. So the limit of f of x as x approaches infinity is also negative infinity. This is as you go to the left. This is as you go to the right. But in both cases, down. Okay. So a sketch of something that's down on both sides, that would look something like this. A parabola opening down. This would be like a parabola opening up. That could be a cubic. And another cubic. Those are the four kinds of end behavior that you can get. Right, so let's type in x to the 4th and see if we can get the end behavior. Eventually, you want to be able to look at a pattern and not have to graph it. But what's the end behavior of x to the 4th? Bob, how would you describe that with arrows? Yep, it's up, up. Or if you wanted to do the limit notation, it would be the limit of f of x as x approaches negative infinity is infinity. And the limit of f of x as x approaches positive infinity is positive infinity. It would just be up and up. I'm just going to write it like that for this one. What about negative x to the 4th? We should know what that negative is going to do as far as a transformation. So what would the end behavior of that one look like? Josh?
Down, down.
Down, down. That's a vertical reflection. So it's going to cause it to open down. If you wanted to write that one in limit notation, that's the one that I did right over here. That would be the answer. So what do you think affects whether it's going to open like down, down, up, 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 down? What do you think you could look at in the problem that's going to tell you that? Well, Annalise, what do you think? Yeah, if there's a negative in the beginning and the exponent, those 2 things are all you need to know to figure out which one of those 4 it is. So you're looking at whether your exponent is an even or an odd, and then you're looking at the coefficient in front of the leading term. None of the other terms matter. So if I'm looking at something like this, you might think, boy, that's a complicated one. It's got a lot of terms in it. Most of those terms don't make a difference to the end behavior. The only one that's going to affect the end behavior is this one. The other ones might cause like twists and turns in the graph, but they're not going to affect the overall end behavior. This is an odd exponent. with a positive coefficient. So positive coefficient is the top row, odd exponent is the second column. That is going to be the end behavior for that one. It's going to go down on the left, up on the right. What's it going to do in the middle? Don't know. That's not what end behavior is about. End behavior is about, if you were to zoom out, what are the two ends of the function doing? Okay, so everything is, as far as end behavior, it's all controlled by the leading term. Think of that leading term. It controls the entire polynomial's end behavior. None of the other terms matter. Just the term with the highest exponent. So in general, that highest term is called the end behavior model. We'll abbreviate it EBM. So if I asked you for the EBM of what I just circled in green, you would say 8x to the 5th. That's the end behavior model. End behavior model is a simplified version of your polynomial. So let's graph f of x and g of x. Okay, f of x is a polynomial. G of x is the EBM. It's the end behavior model for it. And let's see if they look the same. Okay, so they tell me to graph, and they give me the window they want me to use. Let's put in 2x cubed. Maybe we're not going to cube it today. 2x cubed minus 7x squared minus 8x plus 16. And then the end behavior model is just the leading term, 2x cubed. They want me to use a window of -8 to 8 and -100 to 100. Okay, so we'll graph it. And if we look at the two graphs that I just did, do they look exactly the same? Okay, myself? No, they don't look exactly the same, but that's because we're not really zoomed out. The end behavior model and the original one should look almost identical if you zoom out enough. Okay. So yeah, there's some twists and turns happening here, but let's zoom out more. Let's do -40 to 40 and -10,000 to 10,000. So there's the original, and here's the end behavior model. How do they compare now? Yeah?
They're pretty close.
They look pretty close, right? This basically looks exactly the same as that. All those other terms there aren't even making a difference if you zoom out enough and look at the big picture. Okay. So when I give you a function and ask you for the EBM, all you have to do is tell me the highest degree term. What would be the EBM for this one? It's the term I could graph that would basically look exactly the same as the whole thing if I zoomed out enough. Yep.
2x cubed.
So example 8,
sorry.
different question. But yeah, that one is 2x cubed.
-0.5.
Yeah. And the end behavior of that would be down, down. So there's a difference between the end behavior model and the end behavior. The model is a formula. The behavior is when you write the arrows or you do the limit thing. So this is the end behavior. Down, down. And that's 3.2. And we're not going to do that one. So there's questions for tonight. It's all on page 161. And we'll take a look at that first thing tomorrow.